Happy November, happy Monday. We're discussing Stewart section 4.5 today, which is optimization. So optimization problems are simply absolute max-min problems, which we've done before. We did those, I think in section 4.1? But they have possible complications. For one thing, they're presented as word problems, usually. And the variables, the equations, functions are not given. You've got to figure them out. And there may be more than one variable. There may be more than one equation. You'll have to figure out how to deal with that. And then the domain probably won't be a closed interval. So remember, when we did absolute maxes and mins before, we had that nice closed interval method. If you have a continuous function on a closed interval, you're guaranteed there's going to be an absolute max and an absolute min, and you're guaranteed it can only happen at those certain x values. The important x values were the endpoints of the interval and then the critical numbers that are in the interval. But we didn't really come back and revisit the idea of absolute max-min problems on intervals that were not closed. We turned our attention to finding local maxes, local mins, using the first derivative test. Well, we're going to revisit absolute max-min problems, and again, on intervals that are generally not closed, so that's going to come up today. So we'll be learning some techniques for absolute max-min we might not have learned before. All right, the first example is, well, when I say similar to something in my lectures, it's always, the idea is that that's a homework problem. So this is similar to one of your homework problems. And the question is, the goal is to find the point on this line, y equals 3x plus 5, that's closest to the origin. Okay. Well, just as in the related rates problems, you want to start by making a diagram. So notice there's, except for this equation, for the equation for the line, there's no equation given pertaining to how you solve this problem. But it will help to draw, I'm going to try to draw a line with a more realistic slope. It'll help to draw our line. Okay. Now the problem mentions a point on that line, so maybe x comma y is a point on that line. The problem mentions the origin. So those things are actually mentioned, a point on that line and the origin. What else do I need in this diagram? Something that's implicated, but it's not actually mentioned explicitly. Yeah?
The origin, 0, 0.
I already did that. Cooper just woke up. Cooper, while you're asleep, I labeled the origin. Something else. Yeah? Say it again? Well, we could label the y-intercept, sure. What is it? You brought it up. Give it as an ordered pair.
0.
Yeah. Turns out it's not going to be important, but might as well label it because it's easy enough. Did you raise your hand, Jonah? You raised your hand. Yeah.
Is it the x-intercept?
Well, it turns out we don't really need that either. But if we're talking about closest to the origin, closest in what sense? What quantity are we referring to if we're talking about something being closest to the origin? That means we're referring to something that we're measuring. What are we measuring?
Distance.
Distance from the point to the origin. So what we need to add to this is, again, distance is not mentioned anywhere in the problem statement. But what's going to be important in this diagram is this little segment with its distance d. And so so now we can, with our realizing that we need to put that symbol there, illustrate that symbol, that means that we can rephrase the question. So we're going to find the point x, y on the line such that d is minimized. So we've introduced that letter d. Okay, but what is an equation involving d and x and y? I want to wait till I get 5 hands in the air, because we have a point whose coordinates are x and y, and we've got a point whose coordinates are 0, 0. And I want an equation that gives me the d, that's the distance from this point to this point, from high school math. So I want a whole bunch of hands in the air. I want you all fighting over who gets to be picked. Your hand was sort of up.
Yeah.
What's the equation for the distance?
No, I don't want to go. Maybe I'll do it.
You can tap out, but you can pick somebody else who has to answer then. Marie, what's the equation for the distance from this point to this point? How do we do this? Say it again?
Y minus y divided by just 3 times x1.
Oh, that's slope. You're in the hot seat. You always have to answer. Whoever's in that seat has to always answer.
I have no clue.
Well, let's draw a little picture here.
Isn't it radical x2 minus x1 plus y2 minus 1?
Yeah, d is the square root of x minus 0 squared plus y minus 0 squared. So change in y and change in x, each of those squared. Oh, so d is square root of x squared plus y squared. We just have we just have a right triangle. Okay, now will there be a minimum d? I mean, can't I just make x and y equal to 0, 0? Why not?
Because 0, 0 is already equal.
Well, that wasn't the, you said because 0, 0 is already taken, but what's the issue here? Where does this point have to be?
On the line.
The point has to be on the line. So how do we ensure that the point is on the line? What equation do all the points on the line have to obey?
To obey y equals 3x plus 5.
Right, so we must have that point on the line. Since that point is on the line, we know that y equals 3x plus 5. So let's put that into this formula. D equals x squared plus 3x plus 5 squared, all that square root. So that's x squared plus 9x squared plus 30x plus 25 all that is square rooted. So 10x squared plus 30x plus 25 square root. Now, our quest now is find the value of x that minimizes d. So as you progress through these questions, through these solutions, you want to keep rephrasing the question in more specific ways that give you more of an idea of how to solve it. So find x that minimizes d. Okay. Now, remember I said there's, so we notice that we really had two equations, this equation and that equation, and we had two variables, x and y. And we used one of the equations to get rid of the y. So now we have just a single equation involving d and x, so we have d given as a function of x. Great, so we've dealt with some of the complications over there. Now, one of the complications is we're not told the domain. What is the domain of this function, d? Yeah. Why?
Because it's a polynomial.
Well, it's a polynomial sitting inside of a square root, though. All right? So the question about domain is sort of a question of, the question is, what are the good x values? The x values where you will get a good y value or a y value. And you often answer that by thinking, well, what are the bad x values? What could go wrong in this calculation? Well, maybe the thing inside would turn out to be negative, and then I couldn't take the square root of it. That seems like a complicated question. So can we think about, what if the thing inside would turn out to be 0? What would the distance turn out to be? 0. Will that ever happen? No. The distance will never turn out to be 0 because our line doesn't go through the origin. So in fact, in this diagram, the distance d will always be a positive quantity. That's going to be useful to know that this thing always exists and is always a positive number. It's never 0. It's never undefined. So the domain is all real numbers. Now, a while ago I said, previously when we did absolute max min problems, we knew we were going to have an absolute max and an absolute min because we had a closed interval and a continuous function. Oh, dang, we don't have a closed interval. So let's answer this question. Do we expect that there could be an absolute max or an absolute min or both or neither? Could there be a maximum value of d for that diagram over there? Courtney, I thought your hand was going up. Say again? I get to ask the question. You have to answer it. You can't answer me the question. Well, suppose I tell you the maximum d is 1,000,000. Would you believe me? Why not? Just move that point farther out on that line. That line can go as far out as, that point can go as far away as you want. So it seems pretty clear from the picture, my beautiful picture, there is not going to be a maximum distance because you can move out as far as you want along that line. So that's important because we're going to go fishing and we want to make sure that we catch the right fish. We want to catch the fish that's the minimum value of D. And we want to know, what if we pull in a fish, could it maybe be the wrong fish? So where do we go looking to find the value of x that minimizes d? Well, Cooper,
There's a max. There, oh, you can't have a max. There might be a min.
but where do we look? How do we look? Say it again? Yeah, so we're gonna study, we're gonna find d prime, we're gonna find the partition numbers for d prime, and then we're gonna make a sign chart for d prime to figure out where d prime is positive and negative and 0 and undefined. And then use that sign chart to answer our question. All right, so d prime of x is the derivative of this mess, 10x squared plus 30x plus 25. Now this is a chain rule problem, so I think we can, I'm going to march ahead here. The outer function is square root of parentheses, so the outer prime is 1 over 2 square root of parentheses. And then I put my original inner function back inside, 10x squared plus 30x plus 25. But then I've got to multiply by my inner prime. So times 20x plus 30. You notice in your homeworks and quizzes, exams and quizzes, I'm counting off if you leave off parentheses like that parentheses. Every time I do a problem in class, I mention you've got to have these parentheses. All right, so now let's clean this up. I can cancel that 2, and I can put that thing in the numerator. So 10x plus 15 over square root of 10x squared plus 30x plus 25. Hey, does anybody recognize that mess in the denominator? It's d. So this is 10x plus 15 over d. That's crucial because I want to know the partition numbers for d prime. Those are the numbers that make d prime equal to 0 or d prime discontinuous. So what are the bad x values? What would be the x values that would make this not exist? Well, the only way this could not exist would be if the denominator were 0. That would mean that the distance d would have to be 0. What are the x values that cause the distance to be 0? Oh, well, there aren't any. Remember, a while ago we talked about this. The distance is never going to be 0 because that line doesn't go through the origin. So in terms of bad x values that cause d prime to not exist, there aren't going to be any. D prime always exists. How about x, so partition, so I'm going to move over here to this board. So we have partition numbers. For d prime equals 10x plus 15 over square root of 10x squared plus 30x plus 25. And that's 10x plus 15 over d. So there are no x values that cause d prime to not exist. And that's because the distance d, we already discussed, is never 0. So what are the x values that cause d prime to be 0?
Negative 3/2.
Yeah. How did you find that?
I said 10x plus 15 equals 0, and then simplified negative 15 over 10.
Yeah, exactly, because that's the value that causes the numerator to be 0. We have a fraction. We want to know when it's 0. We just look at the numerator. Well, we need to make sure, we need to find numbers that cause the numerator to be 0, but not the denominator. But we don't have to worry about the denominator because it's never 0. So this causes d prime to be 0 because the numerator equals 0. So the partition numbers for d prime are just that one. So we're going to make a sign chart for d prime. And I want to label this sign chart for d prime of x, and that's 10x plus 15. In the denominator, I'm just going to be ornery. I'm just going to say the denominator is d. So we know when x equals minus 3/2, we know that d prime equals 0. So can somebody choose some sample numbers for me to use here? Yeah.
On the left, -2, and on the right, -1.
Okay. So let's do f prime or d prime of -2. I'm going to plug -2 into that formula. 10 times -2 plus 15 over d. Now, all we care about is whether this thing is positive or negative. We've already determined that, or we've already observed that d is always going to be something positive. So this is going to be -20 plus 15 over something positive. Okay, well, -20 plus 15, that's something negative. So I have a negative over a positive, and so that's negative. So out here, d prime is negative. And out here, d prime at -1 is, I'm going to just go ... It turns out to be positive. Okay, so that tells us that there is a local min. We see that d of x has a local min at x equals -3/2. And that's because d prime changes from negative to 0 to positive. So, this technique of making a sign chart for d prime, that's the technique we had for finding local mins and local maxes. Well, dang, we're trying to find absolute min. Well, here's where what I was saying earlier. We have to sort of expand our techniques or sort of generalize our techniques. Notice This tells us that D, if D prime goes from negative to 0 to positive, that means that D changes from decreasing to horizontal tangent to increasing. So that's definitely a low point nearby. That's a local min. So what would have to happen for that to not be an absolute min? Well, the only way that could not be an absolute min would be if the graph somehow later turned around and went down deeper. But that would show up on the sign chart. We see that this graph of D is always going up now. It's never going to come back down. And over here, the graph is coming down from up high. So there will also be an absolute min. Okay, so we found our x value. We just need to find our y value. Its y is going to be 3 times that x value plus 5. So that's minus 9/2 plus 5. So that's 1/2. So the point is, we're supposed to find the point x, y is going to be minus 3/2, comma, 1/2. And that point minimizes D. Now I want to go back and illustrate this on our drawing, just to draw your attention to something cool. Our given line has, what's the slope of this line? Too slow, 3. M equals 3. All right, so our point that we just found is here, minus 3/2, comma, 1/2. In our little segment here, I never did find out what that distance is, but I know whatever it is, it's the smallest it's ever going to be. What's the slope of this line? Cooper?
1/3.
No, almost. Very close. Cooper made a slight mistake, though. Yeah. The slope M is minus 1/3. It's change in y over change in x. So I had to go down, I had to go, let's see. I had to go to the left 3. Well, I had to go up 1 and to the left 3. So 1 over negative 3. So my slope is negative 1/3. What's the product of these two numbers? Negative 1/3 times 3 equals, say it again? Negative 1. What do you know about lines whose slopes multiplied to give you negative 1? What was your hand up? Inverses. The slopes are inverses, negative inverses. But what's that tell you about the lines? Perpendicular. Aha. That's a fact from geometry. If you want to find the point on the line that's closest to some external point, it's going to be at the foot of the perpendicular. It's going to be on the line that goes through that point that's perpendicular to your given line. So this is to be expected. So perpendicular. So that's pretty cool. That's example 1. Example 2. Find the area of the largest rectangle that can be inscribed so to say inscribed in, that means all its vertices lie on the triangle that's 5, 12, 13. In a way that two of the sides of the rectangle are actually lying on sides of the triangle. Two rectangle sides lie on the triangle sides. Okay, so let's put this all together. I've got a rectangle, and it's got to be all inscribed in, so all four of its vertices have to lie on this triangle. And furthermore, two of the sides of the rectangle have to actually lie on the sides of the triangle. Oh, so that means I'm going to have this kind of thing going on. I'm going to have a triangle that does this. All four of the vertices of that rectangle lie on the triangle, and furthermore, two of the sides of the rectangle are on the triangle. What does that tell you about the angles of that triangle? You're kind of grimacing, so I think you've got the answer. What can you tell me about the angles of this triangle if this is a rectangle and it's fitting in here like this?
But the angles, well, it would be a right triangle.
Exactly, that's all, yeah. Must be what are the sides of that triangle? What's the hypotenuse? Why? Yeah, so with hypotenuse 13. So we have 13, and we have 5, and we have 12. How do we check that? Well, let's check Pythagorean theorem. So 5 squared plus 12 squared, that's going to be 25 plus 144, but that's 169, and that's 13 squared. So it turns out 5, 12, 13 is a famous triangle. Other famous triangles are like 3, 4, 5, for instance. Okay, so now, remember I said a while ago, start by drawing a picture. Well, it took us a while to get to a picture. Now this problem mentions the area, so let's add that to our picture. And let's add some other stuff. Let's add this length being x, and let's add this length being y. So what's an equation for the area? Because area is certainly mentioned. X and y weren't mentioned, but it's an area of a rectangle, so it makes sense that we're going to need to work with x and y. So what's the equation for the area A? Yeah.
It's just x times y.
Great. Oh, dang. Not great. I mean, it's an equation, but it has two variables. Can anybody help me out here? Can somebody come up with another equation? Annika, I think that was a kind of a heavy sigh. Have you got the answer, or are you tired of this? Or both? What other equation do x and y satisfy?
It was a sign, I had it, but I blanked.
Okay. Cooper has a hand up. Well, what's the constraint on this point? Remember a while ago, in the previous problem, we had a constraint on our x, y, that it had to be a point that lived on that line. So we had one equation for the distance. We had another equation that x and y had to satisfy because they had to be a point on that line. Gee, it'd be great if we had a line equation. Yeah, Cooper?
We know the area of the triangle is 1/2 base times height. So, and one of the legs of the rectangle is the height of that right triangle on the bottom. On the right.
Yeah, but I want to follow my GPS. So I want to do like a tried and true thing, because I think you might be leading us off into the wilderness. Of course, there are plenty of wacky videos where people follow their GPSs and they end up in lakes. But it'd be great if we had an equation for that line, right? That's our usual thing. That's what we had over here. We have a point that has to live on this line. Can somebody come up with an equation for this line? Let's imagine that this is an x-axis and this is a y-axis. What would be the equation for this line? Y equals mx plus b. Help me out here. Who can tell me what the b is? Caitlin, I thought your hand was up. Sort of up. It's like this. What's the y-intercept for that line? Say again? Did you say 5? Yeah, exactly. So that's 5. What's the slope of that line? Oh, your hand was up. Almost. Not 5 over 12, negative 5 over 12. You got to go down 5 and over 12. Minus 5/12 x plus 5. So same thing we had before. We have, this is unknown, but we want to minimize or maximize a, but it involves 2 letters, x and y. But let's use the second equation to eliminate y. So we have a equals x times minus 5/12 x plus 5. And so that's minus 5/12 x squared plus 5x. Okay. Now, what's the domain of this function? That's, what are the values of x that we're allowed to use? As an abstract function, what's the shape of this graph? Y equals minus 5/12 x squared plus 5x. Your hand is kind of up.
I think it might be a parabola. So
Oh, you can't say I think. You got to declare it. You got to sing it to the hills.
all right.
You're sure.
Yeah.
You're absolutely positive. So it's a parabola for sure. Facing which way? Somebody else. Yeah. Facing down. So it's a parabola facing down. Now, oh, that's good, because a parabola facing down will have a high point. So but thinking about domain, in that picture over there, what are the values of x that we would be allowed to use? You notice this function, a equals minus 5/12 x squared plus 5x, that's a parabola going down that goes on forever. But this is not an abstract function. This is a function that's describing this geometric picture. So in this picture, what's the smallest that x could be? Yeah, and it can't actually be 0 because then we wouldn't actually have a rectangle. What's the biggest x could be? Well, 12, although it can't really be 12 because then we wouldn't have a rectangle. So the domain is a bummer. It's from 0 to 12, but not including the endpoints. Okay, so the function a of x is a parabola facing down. So it will have a max where 0 equals a prime. And what is a prime? That's going to be minus 5/12 times 2x plus 5. So in other words, minus 5/6x plus 5 has to equal 0. So 5/6x has to equal 5, so that means that x equals 6. So that's our value of x, but our question was not to find x or even to find y. Our question was to find the area. Well, let's get our corresponding value of y. It will be y equals minus 5/12 times that x value, 6, plus 5. So that's minus 5/2 plus 5. So that's 5/2. That's my y value. But again, we were not asked to find x and y. We're asked to find the area. So the area is 6 times 5/2. So that's 15. There we go. So again, 2 equations turned up. We mined one equation to eliminate y. And then we ended up with an equation for some quantity in terms of x, and then we maximized or minimized that quantity. Previous problem, we minimized d. In this problem, we maximized a. All right, so example, so box problems. So I want to talk about box problems. So the setting. We have a box with square base and open top. So that's going to be a box that looks like this. So you convey that it has a square base by doing something like this. This is x, and this height could be something else. And then it's an open top, so that's a big void. So box problems, there are 2 flavors. Two types of problem. One is given the surface area SA, maximize the volume. So that would be, for instance, you're allowed to use a certain amount of surface area of glass to make an aquarium. What should be the dimensions that would give you an aquarium with the largest volume with that amount of surface area of glass? Or, given volume V, minimize the surface area. So that would be, given you want an aquarium with a certain volume, what dimensions should it have to use the least surface area of glass? So there's two types of problems. So this first type is a recitation problem for you all to enjoy tomorrow. So in recitation 11, this problem is today. It's our example 3. So we have a box with a given volume, a box with square bottom and open top. So we have a box with a square base. I really write bad when I'm in a hurry. Box with a square base and open top. It must have a volume V equals 32,000 centimeters cubed. Find the dimensions that lead to the least surface area. So find dimensions that minimize the material used. So that is, it minimizes their surface area. Okay, well, our equations are the volume, V, is known to be 32,000. But in terms of those letters, what is that? We've got a box whose base is a square of sides x and whose height is h. So what's the volume of this box? I'd like to get 5 hands in the air. A box with sides x, x, and h. What's the volume of that box? Annika. Yeah, volume is x squared h. Now what about the surface area? SA. What is that? Yeah.
4xh plus 2x squared.
Open top.
Just plus x squared.
Yeah, 4xh plus x squared. The bottom is x squared. Each of these sides is x times h. So 4 of those sides and then just the bottom. And we're supposed to minimize surface area. Okay, look, again, we got a bummer. We've got a surface area equation, but it's got 2 variables, x and h. But we can use the volume equation to eliminate h. Or actually, let's use the volume equation to eliminate x squared. Because, no, let's use the volume equation to eliminate h. So h is going to be the volume over x squared. I'm not going to use the number right now, because I want to emphasize that you should work these problems with letters all the way to the end and then plug in the numbers at the end. So the surface area is 4xh plus x squared. And so that's 4 times x times the volume over x squared plus x squared. And so that's going to be 4 times the volume over x plus x squared. Okay. Now I want to race through the end here. I want to find the critical numbers and make a sign chart for SA prime. So find the surface area prime and make a sign chart for the surface area prime. Okay, so surface area prime, that's going to be the derivative of 4v over x plus x squared. Now, if you go through this, you don't need the quotient rule. This is the same as 4v times x to the minus 1. It turns out that the derivative of this is minus 4v over x squared plus 2x. So notice that this is undefined when x equals 0. And we want to find out when the surface area prime is equal to 0, well, 0 has to equal minus 4 times the volume over x squared plus 2x. So that means 4v over x squared has to equal 2x. So 4v equals 2x cubed. And so x cubed equals 4v over 2, in other words, 2v. So that means that x is the cube root of 2v. Well, now we can plug in the numbers. The cube root of 2 times 32,000. Oh, so that's the cube root of 64,000. Well, the cube root of 64 is 4, so this is going to be 40. 4 cubed is 64. 40 cubed is 64 with 3 zeros. I'm going very quickly here. But I want to get to the point where we see that that's the only place where a max or a min could occur. But we don't know if this is a max or a min. We just know this is the place where SA prime is equal to 0. It's the only place so can we reason as to whether we think that's a max or a min or neither? Well, if you make a sign chart for SA prime is that mess minus 4 times the volume over x squared plus 2x. And you make that sign chart does not go past x equals 0. You can't have a box whose base is 0. That wouldn't be a box. So it has to be x is greater than 0, and this critical number is x equals 40, and that's where SA prime equals 0. If you choose sample numbers, you find out that SA prime is negative, and SA, the surface area prime, is positive out here. You'd have to actually use the formula for the surface area to use that volume as the number, and it turns out that that tells us that that's the location of a min. And then the corresponding, we need to have the height as well. We need the dimensions, not just x. So the corresponding height is well, we know that the height is the volume over x squared, so that's 32,000 over 40 squared. So that's going to be 32,000 over 1600. So the bunch of zeros are going to cancel. That's going to be 320 over 16, so that's 20. So the dimensions are 40 by 40 by 20 for the dimensions of the box. I went really quick with this example. I'm sorry about that, but I wanted to push through to the end because this is a harder one than what you have in your recitation. It turns out that if you decide what the surface area has to be and you want to maximize the volume, your equations are quite a bit simpler. All right, if you didn't sign in, make sure you find the sign-in sheet and sign in. Have fun tomorrow recitation. I'll see you on Wednesday. Oh, we're over time.